Well, welcome everybody. Thanks for coming to my talk. Today I will present a tool that I've built, or we have built here at ThinkCell, that makes it easier and more convenient to build web applications in C++. And I saw in the list of participants that Yegor Zuborov is also listening to my talk, and he was the one who started the tool when he worked here at ThinkCell. So thanks, Yegor. Thanks for letting me take this over. Before I go into the details on that tool, let me start by sharing a little experience I had developing a web application recently. So, sorry. That didn't work well. So, usually at ThinkCell, we develop a product and we only work in C++. And our product is an add-in to PowerPoint, but I tried to build a small extension, which was a web extension. So it was a web application. It was a small extension to our product. So here you see the website of Tableau.com, which is an online data visualization tool. And we wanted to let users import visualizations they had made on that website into PowerPoint. So I can show you how that looks really quick. So you see here the user has Chrome open. He has a small Chrome extension. And with that Chrome extension, he can select a chart on the Tableau.com website. So he selects the chart. Now the web application opens. And now the user can map the data that he has on Tableau to the categories and series of a stack chart and to the values of a stack chart. Now he creates the chart, PowerPoint opens. And if we wait a second or two, then the chart will appear as a PowerPoint chart. And it will remain linked to the Tableau website. So if the Tableau data changes, then the data in the chart can be updated. So that's essentially the feature. The web application is tiny. There's a few hundred lines of code, maybe. But developing that application, had one challenge. There was one interesting piece of code in that entire application. I have to transform the data that comes from Tableau into the tabular format that I need to create a chart. So the data I'm getting from Tableau is a long list of individual data points. Each data point can be either a number or a string or a date, for example. So I have to sort all the category values. I have to sort the series values. I have to make them unique. And then I have to do a sequence of binary searches so I can find the right place in my data table where each individual data point must go. So not terribly exciting as a coding problem, to be honest. But it turned out that developing this in JavaScript, or rather in TypeScript, which is what I used, that turned out to be surprisingly difficult. So first, I want to sort an array of data. So I look at the documentation for sorting a JavaScript array. And the documentation says that by default, sorting an array will convert all the elements into strings and then compare them by their UTF code unit values. That is really surprising if you're coming from C++. But OK, we can fix that. We can supply our own comparator to sort. What is worse and not easily fixed is that the time and space complexity of the sort cannot be guaranteed. If you've seen Kevin Henney's keynote, for all we know, it could use Bogo sort. Now, sorting is weird, but to make matters worse, there's also no make unique algorithm, and there's also no built-in binary search. Now, of course, the experienced JavaScript programmer would say, well, that's not a problem. I just go to the npm repository and look for a nice binary search implementation. So I did that. I looked. And I have still problems with my mouse here, so this is how it looks. I looked for binary search in the npm repository. There are a surprising 316 results. And so the second one you see here is actually binary search. And it's actually not the one you should use. So it's the one that npm thinks it's best. But at the very least, it has the common problem that the implementation would overflow if your array gets very large. I don't remember, was it also Kevin Henney's keynote? It was in some other talk. So the most common bug when you're programming binary search. So I really didn't want to program this in JavaScript. I wanted to program my little web application in C++, because in C++, everything would be so easy. My data value would be a variant of double, string, and a time point. I could create a vector of those data values, fill it with the results of my Tableau query, and then thanks to the C++ range API, I could sort that vector, and then I could get the range of unique values in that vector. And on that range, I could do binary search, and I don't think that binary search would overflow on large ranges. So this is how I want to program my little web application. For one thing, the standard library, as you can see here, is very strong. Second of all, it's the language that I'm most familiar with. So it would be a big productivity gain for me to program my web application in C++. And last but not least, there also might be some code I can share. There might be code I could share between my main application and my web application. And indeed, that was also a case here with us. So what do we need to write a web application in C++? Well, we need three things. First of all, we need to compile C++ so that it can run in a web browser somehow. Then we want to have a way that we can call JavaScript from C++ because we want to manipulate the website. We want to manipulate the DOM tree, for example, and the JavaScript APIs are the way to do that. And last but not least, ideally, we want those calls to be somehow type safe, just because that's what we are used to from C++. We need to compile anyway. It would be nice if that compilation step would give us anything back. So how do we do those three things? How do we get C++ onto the web, first of all? That's where WebAssembly comes in, of course. And WebAssembly and its predecessor, ASM.js, are not exactly new technologies. They've been around for quite a few years. So there have been a lot of great talks at CppCon about them, and I'm not going to repeat everything that they said. So this is going to be this is probably not even the entire list, but it's a very good list. So this is going to be the shortest introduction to WebAssembly at CppCon ever. So WebAssembly is a binary format, of course, which we compile to. It has been standardized and is supported by all major browser vendors, which, if you're familiar with web technologies, of course, is a huge step forward. It's a very fast and compact binary format that supports 4 low-level data types, integers and floating point numbers, essentially, in their 32-bit and 64-bit variants. And each WebAssembly application, each WebAssembly module runs in its own sandbox. Its interaction with the environment is extremely limited. It's by default essentially none. Not only can it not interact and disturb the environment, but by I don't know, messing with the operating system, it runs in an application sandbox inside the browser and can't even interact with the browser by default. But on top of that, each WebAssembly application has its own little piece of memory that is also by default private to the memory module. So you can imagine they actually have their own little array buffer of bytes that each application carries around with them. WebAssembly modules are instantiated from and can interact with the JavaScript environment if they need that. So here on the left, we have a WebAssembly binary. It has a function A. And on the right, we have the JavaScript world in the browser, which has a function B. And now the WebAssembly module can declare that it wants to import that function B, and it wants to export the function A. So now the WebAssembly binary and the JavaScript environment can call each other. There's one important limitation here, and that is that the function A and function B are limited to the data types that WebAssembly supports. So they can only have return values and arguments that are integers and floating point numbers. And you can see here that WebAssembly can also export access to its memory object to JavaScript. So then JavaScript can access that as well. One important comment, I will do the Q&A at the end of my talk. So feel free to enter questions in the Q&A panel, and I'll go over them at the end of my talk. There are slide numbers in the bottom. There's a raised hand. Maybe is there something important? Some understanding question I should answer right now? Antonio, or was it by accident? No. Excellent. Sorry. Okay. All right. They can call each other, yes, and they have to have integer and floating point arguments or return values. That's an important limitation here. So how does that look in code? Now my clicker is gone again. Okay. How does that look in code? Also pretty simple. We define two JavaScript functions here, abort and handle Stack Overflow, that we will supply to our WebAssembly module. Both will simply call abort in JavaScript, print an error message to the JavaScript console. We create a map of those imports. Then we instantiate the WebAssembly module with the binary that we have downloaded from somewhere. And we get an instance back, so a linked instance of our WebAssembly module. And we can call the exported functions on that WebAssembly thing. And as I've shown, showing in the link below, this kind of simple interaction calling each other's function is pretty small. So they live somehow in the same part of the browser VM world. Okay, WebAssembly also comes with its own, with a defined text format that makes it very easy and relatively convenient to debug WebAssembly programs, a bit like you're debugging disassembly. So this is the text representation for the string compare function from the C runtime. And here the two parameters, parameter 0 and parameter 1, they would of course be pointers to zero terminated strings. So they would be pointers to locations in the WebAssembly memory buffer that the WebAssembly module has. And just having a binary format is not enough, of course. We need some more toolchain support to get C++ into a web browser. And that toolchain and runtime support is provided by emscripten. So emscripten ships with a compiler, which is clang. Clang has a WebAssembly backend. And emscripten is a set of runtime functions that let us do useful things from C++ in WebAssembly. And those runtime functions let us access input devices, create graphics, create audio output. So emscripten provides an interface for the simple direct media layer API and maps that to browser technologies. And if you're not using the STL library, then you can also use the OpenGL API from C++, which emscripten maps to the WebGL APIs that the browser supports anyway. And emscripten also lets you access the HTML5 input events from C++. And last but not least, emscripten also provides the standard C APIs to access a file system for accessing essentially a virtualized file system. So you can ship some files with your module and access them as if they were on the disk somewhere. Okay, this is great if you are developing a portable C and C++ application like a game. Then that's all you need. You need to output graphics, you need to create audio, and you need to access your input devices. And thanks to emscripten and before that Asm.js, it has become relatively easy to port such applications to the web, and that by itself is already pretty impressive. So that's Doom 3 running in the web browser on my old laptop. Okay, so we can make a check mark here. We can bring C++ into web applications. We know how to do that. Now, how can we call JavaScript from C++? Well, we have seen the first way already. We can simply import JavaScript functions in WebAssembly and call them, as long as those functions only have integer and floating point arguments and return values. So that's one way. Emscripten provides an interesting other way. You can directly embed JavaScript code into C++ code if you surround it with that emAsm int macro and its variants. So everything in that macro, in that emAsm int macro, the console log and the return, is all JavaScript code, which will be called at that point in our C++ code. And in that example I've printed here, you can even see that we can pass data to that JavaScript snippet and return data back from it. But that data is also limited to integer and double return values, of course. So it's convenient, but has the same limitation. Emscripten has another interesting way, which is called the mbind API. It essentially is provided by the emscripten value object that lets you translate literally JavaScript to C++. So here in that example, we are accessing the audio context API from JavaScript. So we are getting a reference to the global audio context object. We are creating a new instance of that audio context. Then we call the create oscillator functions. All these things exist in the JavaScript world. And then we set the type property on the oscillator to triangular, and then the frequency to something which is hopefully middle C. Okay, so that's relatively convenient. It's a literal translation almost from JavaScript to C++. Well, that API has one big problem that you see here. We are calling a method, a JavaScript method, where we are supplying the method name as a string. Then we have to compile that code because it's C++ after all. But that compilation step, that does not give us any type safety. That string will be passed to JavaScript and then it will be interpreted. Hopefully that method actually exists. We didn't make a typo. We also don't know if it takes any arguments that are not optional. And here we even supply the return value as a template argument. So that is not ideal. It essentially combines the disadvantages of JavaScript and C++ into one. We have to compile it, which takes quite a while before we can try it out. But that compilation step does not give us anything back. Still, it is impressive that this works at all. Let's take one moment to check how that is actually implemented, how that actually works. So from my last few slides, you can probably guess that this emscripten functionality is also based and implemented based on some JavaScript functions that are imported into our WebAssembly world. These JavaScript functions let us create new objects, translate C strings to JavaScript strings, or call methods on JavaScript objects. So what do they do in a rough overview way? So the emValueObject method, that's the first one. These are all private. I'm just explaining how the emscripten runtime actually does things. That's not how you interface with it, really. So the emValueObject function is implemented in JavaScript, and it simply creates a new empty JavaScript object. So a JavaScript object without any properties, without any members. And it creates a reference count for that object. And then it stores both the object and the reference count in some map and returns an index to that object, a handle that object, if you will, to the C++, to the WebAssembly world. So that return value here, that emval, is an integer, as it has to be. And that integer is a handle that corresponds to the index of our object in some map. Now, emval new C string is similar, but even more complicated. It would convert a zero-terminated C string to a JavaScript string. And in order to do that, the JavaScript function has to read the C string from the WebAssembly memory object. So it takes the pointer to the zero-terminated string and then reads that C string character by character from the WebAssembly memory object and appends it character by character to a new JavaScript string. Again, that JavaScript string will be stored in some map with a reference count, and a handle to that string will be returned. So that's already quite a bit of overhead there. And if you have those two things, then there are all kinds of other things you can do. Of course, you can write a function that would increase the reference count, decrease the reference count, or call a method on one of those emval objects, of course. Okay, so now we know that we can call JavaScript from C++. Thanks to emscripten. Now we would really like something better. We would like to make those calls in a type-safe way. So how could that look? Let me show you in a small example. So let me first show you here that I'm not faking anything. So I have a little first example, and you see that it's empty. It doesn't do anything yet. So you have some code, which is JavaScript code in the comments. And I would like to translate that to C++ to show you how that could look. So I'm creating the element, accessing the global document in JavaScript, call create element, and create a new paragraph element. Then I set the text of that element, Again, this has to be a JavaScript string, hello CppCon. So I want to set the font size so you can also read anything. And last but not least, we put it onto the website if I can type. So, okay, that should do the trick. Let's compile that. I don't see what I'm typing. No, that's gonna work. Okay, so that's going to take a minute. Oh, I get a compiler. My first live demo at a conference, and now this. Okay, so what it says here, no matching member function for call to font size. Okay, candidate function not viable. So this is the thing I'm calling. And the font size does not take a double, but it expects a union of either null for some reason or a string. Well, good that we had a compiler that catches that. This is, so now I remember, this is the cascading style sheet font size property. And I always forget that this takes a string because it needs a unit as well. So this is how it should be. Okay, let's try that. Fingers crossed. Okay, that worked. Cool. So let's go back to Chrome. Let's reload that, and there you go. Hello, CppCon 2021. Oh, that was really good that we had a compiler there. That would have been embarrassing. So what just happened? Well, you saw our tool in action, of course. There are online repositories of interface definitions for JavaScript libraries that are written in TypeScript. So they are type annotated descriptions of JavaScript libraries. And we can download them, call our Typescripten compiler on them, and the result is that we get a C++ header file with a type-safe description in C++ of an existing JavaScript interface. And then we can compile against that, we can program against that, and if we do a mistake, we get a more or less useful compiler message. So what is TypeScript here, and what are those type definition libraries? Well, let me show you a small example. So this is an excerpt from the type definition library for the standard JavaScript DOM API, more specifically for the document object that I've just used as well. So this is TypeScript, if you're not familiar with TypeScript. So we have document interface, and the document has a URL property, for example. That URL property is marked read-only, so I cannot set it. It must be a string. The document also has an active element, which is an element, so that's essentially an HTML element, or it can be null. That's good to know. And the fourth property is the document title. It's also a string, but importantly, I could set it. So that's also good to know. And TypeScript ships with type-safe type definition libraries for the standard JavaScript APIs. But not only that, but as part of the official TypeScript project, there's a large GitHub repository of type definition libraries that is community-driven, and that contains now type definition libraries for over 7,000 JavaScript libraries. So for all of those, we get type descriptions, essentially. That contains popular JavaScript libraries like Angular, Bootstrap, or Tableau.com, which is the one that I needed. TypeScript not only ships with those type definition libraries, TypeScript also ships with a super convenient parser API. So this is essentially all the TypeScript code that you need to read one of those interface definition files. So here in the first line, I create a TypeScript program from a file from an array of files technically, that instantiates the TypeScript parser, will read all the dependencies, does essentially all the work. And then I can get a handle to the parsed source file, and I can iterate over all the syntax nodes in that parsed source file and can ask the TypeScript parser API, is that node a function declaration, or is that a variable statement? If it is a function declaration, I can check what's this function's name, what is its return value, what are its arguments and their types, and so on and so forth. So this is extremely useful, and this is actually enough to build a compiler that translates interface definition files to C++, of course. So this is what our Typescripten tool does. You can check it out on GitHub. I'm very interested in more contributors. You can check it out. You can ask me questions here at the conference or later on Gather. So it compiles TypeScript interface declarations to C++ interfaces. So the goal is that you can write type-safe and idiomatic C++. So it looks more or less like the JavaScript code you would have written. And it is based on emscripten, hence the name. So we use the emscripten runtime for that. So where in JavaScript you would maybe assign a string to the document title, in C++, you can get a reference to the global document object and then call its title setter and pass a JavaScript string. So roughly similar in spirit, so to say. So this is a bit like a simplification of what our generated interfaces look like. So I've said they're all based on the emscripten runtime. So that's what we use. So that's what all the objects essentially derive from, what all our interfaces derive from. But thanks to the TypeScript interface definition files, we can write a type-safe wrapper around the not type-checked emscripten API. So we know the document has a title property. We know that it's settable, so we can generate a setter. We know the type of that property is a string, etc. Okay, so this is a bit how it looks. Now, if you're parsing TypeScript, then you have to ask yourself, okay, do we have to support all of TypeScript's constructs? TypeScript is a pretty flexible and very complex language because it's meant to annotate JavaScript in all its flexibility and complexity. This, for example, is valid TypeScript. So here we have an interface A, which has a function with an argument A. And that argument A has to have a type, but the only requirement on that type is that the type of A must have a property length. Okay, that's a pretty interesting statement. That would be hard to translate to C++, probably. It would be possible maybe for that single property. I think you can write some type trait to check if some type has a length property. But supporting that in all its generality for all kinds of properties, that would be pretty hard, I guess. Luckily, we don't have to do that. We need to support the common TypeScript constructs that we actually find in interface definition files, and then create useful, meaningful C++ from them. So in that sense, in that example, most programmers would not write it like that in an interface definition file. They would maybe have simply written it like that. And that's something that we can easily translate to C++ because now that type just has a name, and we might derive from it in TypeScript or something like that. So that being said, there are a large number of TypeScript constructs that our tool already supports. So of course, we support all the built-in types. We support any, undefined, null, string. We support types with optional members. We support type guards, which are a TypeScript feature. They are a mixture of a type check and a built-in cast. We support TypeScript union types. We support mixed enumerations. We support passing C++ functions as callbacks or C++ lambdas as callbacks to JavaScript. And we also support generic types in TypeScript. As of a few weeks ago, our tool is self-hosting. That means it understands enough TypeScript features so that we can completely parse and translate the interface definition file for the TypeScript parser itself, which our tool uses, of course. So we don't need any hex anymore to parse TypeScript. So that means that this little snippet of TypeScript code that I've shown you before can be translated to C++ almost literally. And in C++, it would look like that. So except for some namespaces, it's really the same. And it's slightly more complicated to create a JavaScript array. And you see here in the highlighted line, one example of how we pass a C++ lambda to JavaScript or to TypeScript so that it is called as a callback for each syntax node that the TypeScript parser will encounter. Okay, we'll see a bit more how that works on the next slides. So you can imagine that if you're translating one language, in that case TypeScript, to another language, to C++, there are quite a number of interesting challenges that come up because the two languages are very, very different. Sometimes those differences are relatively simple. For example, in TypeScript, the declaration order of your types does not matter. So this here is valid TypeScript. I can define the type foobar as the union of test foo and test bar before either test foo or test bar are even declared. So we cannot parse that and translate it literally to C++ in the same order, for example. That would not be valid C++. But we have to collect all the types and then reorder them in some meaningful order. So let's say base classes before derived classes, template arguments before the templates. Yeah. So that's one challenge, one obvious challenge. Other interesting features. TypeScript has what I said are union types. Those union types are not at all the same things as C++ unions. So for one thing, they don't have a discriminating enumeration value. So you can't ask that union type, are you A or B or C? You can cast them to each of them, but we have to know which one it is before that. Instead, you can think of that union type as being all of those types at the same time. So that means that union type A or B or C is the type that has the same properties that A, B, and C share. So in that sense, it's not a union, it's the intersection of properties, confusingly, I might say. Okay, so that's interesting. Not only that, but that union type A or B or C, or a value of that type, is constructible from any value that has the same set of properties. So here in my little example, I'm creating a new type D, doesn't have any relation to A, B, or C, but it has the correct property, that's the common property. And I can assign a value of type D to a value that has the union type of A, B, or C. Okay, that's surprising again if you're coming from C++. But in JavaScript and TypeScript, a type is not the same thing as in C++. A type is not defined by its name or by its inheritance relationships as in C++. The type is really defined by the set of properties it has. And any other object that has the correct set of properties satisfies that type as well. This is what it's called structural typing. So the structure of the object defines its type and not really its name or anything. Okay, so what do we do with that in C++? C++ does not support structural typing. Still, there are a number of meaningful things that we can express in C++ that are still correct. So for example, we could say a union of A, B, or C can convert to all the common base classes of A, B, and C. That would certainly be correct in TypeScript as well. We could also say a union of A, B, or C can convert to a wider union of A, B, C, or D, because by adding D, the set of our properties must certainly not get larger. It might stay the same or get smaller. So that conversion is also valid and expressible in C++. And we could also say that such a union of A, B, or C is constructible from anything that can convert to A, B, or C. Also valid C++ and valid TypeScript. But it sounds like what we're expressing here is much less than TypeScript would permit, and that's certainly correct. But in practice, luckily, again, this is not as limiting as it sounds, because we don't have to support all of TypeScript, just the TypeScript that we find. And in practice, what I find, for example, in the TypeScript parser interface definition itself, a lot of programmers would write that. They would not repeat the same property 4 times and then hope the TypeScript compiler finds out that they're all the same type. But they would encode that in some inheritance relationship, actually, that we can translate perfectly to C++. Pooh, there we are. Lucky, I guess. So the last TypeScript feature I'm mentioning now are those mixed enumerations. Also interesting. TypeScript supports enumerations where the enumeration options can be strings or doubles or integers, of course. And here we support that in an entirely different way. We said, well, we translate that as a normal C++ enumeration. It's just an enum class containing options foo and bar. What we can customize is how we marshal that to the JavaScript world. So we can say, let's define some template lookup type marshal enum that contains a map. And in that map, we say, well, value foo should be marshaled to JavaScript as a string, and value bar should be marshaled to JavaScript as a value, as a double, actually. So and then we have solved that problem. Now, I've also mentioned that we do support function callbacks so that we can pass C++ functions to JavaScript. And let me also show you how that looks. Again, I have a little example prepared. So I have this messy website, and I would like to clean this up. But the button doesn't do anything yet. We have to program this callback. And luckily, I have prepared something already. So I would like to write this click handler. Here I look up my button by its ID, and then I want to set its click handler. And I have a C++ function on click. That would do the work. Let me show you quickly how that works. So it's the click handler. It takes a mouse event. In that function, I get all the diff elements, and then I get an HTML collection of those elements back. I do a for each over that element of JavaScript objects, over that JavaScript object itself, because of course I've written an adapter for that, and I can just do tcc for each over that. Each element here can be null for some reason, so I take the diff elements that are not null, put them in a vector. Then I sort them, so here I do the actual work. We're using the thing cell range library here. So we sort the vector and compare with less predicate and compare all the diff elements by their height. And that sounds like it's doing what we wanted to do. And last but not least, I go over that vector, that sorted vector, remove all the HTML elements, and append them in their sorted order again. Okay, but this is not going to work. Here on click is a C++ function pointer, and I cannot pass a C++ function pointer to JavaScript. I have to create a JavaScript function object somehow. And we do that by generating a bit of code that for now, unfortunately, we have to hide in some macro. So here we have a little object. We cannot create global objects because the global objects are needed by emscripten. Let me do that. Okay, so it's the onClick callback, so that we are going to generate a member onClick, a member object, and that will wrap our callback. And that callback has the same signature as before. Okay, so it looks a bit like a function. It does some magic. We'll go over in a second. Okay, so that should work. Okay, we pass our onClick object, which is now hopefully a JavaScript object, to the onClick handler. Let's compile that. Oh, now I did actually have a mistake. That's unfortunate. Should not have copy constructs. Why does that have a copy constructor? Now I am super surprised. Well, that doesn't work. And I will go over that. Let's come back to that a minute later. I have my cheat sheet here. I think I did the right thing. Still, it doesn't work. That's the danger of live demos. It should work, but it does not. Okay. What should have happened? What would I like to tell you now? So in JavaScript functions and in TypeScript by consequence, function objects are reference counted objects. They are objects like all the other objects. So we can pass them as callbacks to our event listener. And that looks super convenient, looks super simple, but it has a lot of complicated implications. So the function callback, the event handler will keep alive our callback object. Our callback object will keep alive our own object, some button here in my little cone example. So everything is held alive by something else. There's no real ownership in reference counted languages typically. So that makes thinking about states really, really complicated. So how do you really know in which states this thing can still be called because somebody kept all your objects alive and you don't know who that is? That's what makes JavaScript programming relatively complicated. Luckily, we have a great solution in C++ here. So it's a great advantage when we're moving our web application to C++ that suddenly we get this. Suddenly we get a destructor, that will be called at some deterministic place in our location in our code. And in that destructor, we can do cleanup. We can remove the button, or we can destroy that thing and make sure that nobody can call our callback anymore. So that can be an advantage. And that's something I'll show you now how that works, what's hidden behind that slightly ugly macro. It's a clearer state machine, so to say. So how do we create function objects that we can send to JavaScript and get called back into the C++ world? So here is the description. Here is our onClick object. So that's the thing that will be passed to JavaScript. That onClick object has a function type, a JavaScript function type. And we pass it two things. We pass it a function pointer to some static function, and we pass it the this pointer of our current object. And this function object will directly call into the JavaScript world. It will call a function we provide in JavaScript. And that function receives this static function pointer, and it receives the this pointer. And it captures those two values and does nothing more but create a JavaScript function object, the JavaScript function object that we need, that will also capture the function pointer and the this pointer. And when that JavaScript function object is called, because our button is clicked, then this function pointer and the this pointer and the function call arguments will be passed back to the C++ world. And now this JavaScript function object has another interesting member, another interesting property that we will exploit to clean up our state machine a bit. It has a detached function. So we can detach from our JavaScript function object when our C++ function object goes out of scope. So when that thing is destroyed, it will call this and deregister from that JavaScript function object that lives for as long as JavaScript thinks it has to live. So in that JavaScript function object we have created here will be passed back to C++ as an emscripten value as anything else is. Okay, so now what happens when that JavaScript function object is called and we call back into the C++ world? Well, there's a single entry point, a single call function that gets called, and that has one single task. And its only task is to cast the function pointer to the correct C++ signature and call it. And when we've done that, we are back in our generated onClick wrapper. And that wrapper function has one other task. It can cast the this pointer to the correct type, and it can unwrap the array of call arguments because it also knows the correct signature of our onClick function. And then it can actually call the user code that we wanted to call. So quite a complicated machinery just to make this work. Okay. Now there's one other interesting feature that was just hidden in this in my last code example. And you saw here I created this HTML collection of elements. So here we have a C++ template of JavaScript objects. And TypeScript supports something that's the same thing as templates. So TypeScript supports generic classes, as they are called. And generic classes can be easily translated to C++ templates. They are semantically the same thing. So our compiler supports that as well because it's an extremely common feature that we needed pretty early. Those generic classes can have constraints in TypeScript. For example, we can say that an interface A has to have a type parameter, and that type parameter has to be an option of an enumeration. And we can express that in C++. That's the same as having a C++ struct that has a non-type template parameter. So it's templated on an enum value, essentially. And we can make that translation already. That's also pretty common in some interface definitions. TypeScript supports other interesting constraints that we're still working on. So you can, for example, also say this in TypeScript. So it looks like TypeScript would say here that T should derive from Node, but what we've heard before, structural typing and so on, it only means T must have the same properties as Node. But still, we can express it in C++ as something like that, where we enable a template A if T derives from Node, because just that's as close as we can get to the semantics in C++. This is something that that is still work in progress. Okay. Now I want to show you one other thing, because I also originally wanted to show you that we not only support how do you say the built-in JavaScript libraries, but we can work with all the JavaScript libraries that you can find online. And I want to show you how convenient that can be. So let's leave that example of shame that I can't think about now. So what we can do, a bit like I showed on one of the slides, we can simply install using npm the type definition libraries for Tableau, for example. So there's an add types namespace on npm. It contains the definition of the Tableau JavaScript types. Okay, cool. So we already did that. Now we can go to our third example. Now I have to reference those Tableau types somewhere in my build definition. And without going into our build setup here, I did that already. So here I have some inputs to our Typescripten compiler, and you see I want to compile the Tableau data types here. And now that I have done all of that, I can simply use the Tableau API from here, from C++, in a type-safe way. So I call the constructor of a Tableau visualization. I have to look up the element where Tableau should insert its visualization. And I think I just called that Tableau meaningfully. And then I just have to pass it the URL that tells Tableau where to find its visualization. So let me put a semicolon here. And now pray for me that this works. Okay, that worked. Lucky me. So we can go to my third example, reload that. And now you see the Tableau visualization loading about some musical that at least the Americans in the audience have certainly heard about. So that's all pulled from some Tableau visualization. Okay, so that was just a simple example to show you that we can interface with any JavaScript libraries, really, that we can successfully compile, that is. Okay, so that's almost concludes my talk, and we still have time for questions. So we can make type-safe calls to JavaScript thanks to Typescripten. There's one important disclaimer here. Our tool will be maybe not completely obsolete, but less important when the WebAssembly interface types proposal makes progress. That's a proposal that aims to express JavaScript higher level types in WebAssembly so that WebAssembly can directly make those calls to JavaScript libraries. But still, that's in a very early phase. There's no implementation for that. So we have what we have. One word, and I'll shorten that so we have more time for the questions. I said I use the emscripten API to make calls to JavaScript that I'm just generating type-safe wrappers for, essentially. And I've also mentioned that this emscripten API has a pretty higher runtime costs because I'm passing strings. Those strings have to be translated to JavaScript strings, and those JavaScript strings are then used to look up the actual objects. And I wanted to know how high the cost of that runtime is versus using directly imported JavaScript functions or the emscripten macros I've shown you that can directly embed JavaScript code. And it turns out that the cost of that runtime is pretty high. And it's nothing that would worry me in the first version of our little tool, but it's something that in a future version we should probably optimize, maybe directly generate C functions that we can link against passing so many strings around. Okay, and that's it. There are some open challenges that we can skip for now that would be necessary to implement for a version 1.0 of our tool. But the tool is already useful. We use it already, and all the examples in my code would have worked in theory. And you can check it out on GitHub. Yeah, contributors are very welcome. Just drop me an email. And with that, I am open to questions. Okay, and I see there are 2 questions in the Q&A. Live demos going awry. Yes, you can practice them. You can practice them a million times, and still you did something wrong. Have you considered using concepts to implement support for structural typings? Yeah, actually, I did think about it now that I had time to think about anything because I had to prepare the talk and program quite a few features so that I can say that the tool is self-hosting. I did think about what concepts can do here, yeah, and if I can check some of those things with concepts, but I haven't investigated that to any really serious degree. But yes, it's one thing I thought about. But really, it really hasn't been a problem so far. So I think one of the goals, and I think I have that as an open issue on GitHub, is that for the higher level libraries, so let's say parsing Tableau was super easy. It's a simple library. Nobody did any TypeScript magic in the interface description for that library. So that was super easy to parse. We did that a year ago, I guess. But there are also TypeScript descriptions for the most basic JavaScript types. And the further you go down, the more basic the types get that you describe in TypeScript, the crazier the TypeScript has to become to describe them. So currently, for example, there are some basic JavaScript types where we have hard-coded support for. So arrays, for example, read-only arrays, the function type, the promise type. These are all types that we coded in C++ with their correct interface, and then we just emit them where we need them. But of course, there is a TypeScript interface definition file for those types as well. But I cannot parse that one yet, but I would like to. What resources on WebAssembly? Is there a single book? No. Yes, CppCon videos. I mean, it has been extremely useful, of course, to watch the older talks, even the ones from 2014, where the inventors of SMJS and emscripten essentially talked together. No, I don't have their names ready, and they presented both tools, because all the things they said are essentially still valid in a lot of ways. So no, I don't have a single book. I don't, books, no, and resource also no, except CppCon videos. Have you shared your efforts with the emscripten project? Not yet, but that's of course something that I would like to do, because I thought, well, that's something that, first of all, really surprised me, that they don't have any interface for the standard JavaScript libraries. And the interfaces that they did write by hand for, let's say, the input APIs, they are not very pretty, let's say. And they are not very idiomatic C++. Let's put it that way. Pretty is a bit subjective. They're neither similar to the actual JavaScript API that you are familiar with, not are they idiomatic C++. So I think a tool like mine could solve a lot of work to just expose all the APIs, and then let's say, boom, you have them. And by integrating it into emscripten, it will probably be way easier to generate a more performant call mechanism, except of all these strings that I'm passing around. And Yegor, yeah, lucky. I'm glad that you had a question. What is TypeScript used for? Things so. We use it for the tool that I've shown you initially, or I have that port ready, and it's waiting for me to touch it again. So I ported the little bit of TypeScript that we had to the first version of TypeScript that Yegor wrote himself in the last lockdown, last year, 2 years ago. I don't remember when that was. And then there were still some issues where we had a lot of workarounds. That, for example, we didn't support generics. That I think was one of the big ones. And then I tried to work on the compiler a bit, and then I can throw some workarounds out again. And now I have to check where I would be, so that we can actually use build our little web application, WebAssembly. Is exception handling a WebAssembly limitation? Yes. Yes. Now, I haven't become a WebAssembly expert all of a sudden, but I think that is still in progress. It doesn't, by default, they just don't support exceptions. I think there's some very limited feature where you just throw something in JavaScript, but practically speaking, WebAssembly does not support exceptions. Yes. Exactly. Great question. Thank you a lot for the questions. Did you debug WebAssembly? Yes. Yes. Also a great question that I can answer, I think, in practice, because I tried that out. That's a field where a lot of things have happened. And again, okay, you have to throw us out. Yeah. Yeah. Okay. Thank you very much. Thank you everybody for coming.